In this module, we will cover some fundamentals of intensification of tropical cyclones. Much debate remains in the scientific community about many of the fundamental aspects of tropical cyclogenesis and intensification, and this is reflected in the slowness at which model forecasts of TC intensification have improved over the past couple of decades. This topic itself could probably merit an entire course, so devoting only a single module to TC intensification barely scrapes the surface of the broad ongoing scientific debate about the dynamics responsible for TC intensification. As we've seen in a previous module, one of the governing principles for TC dynamics is that angular momentum is conserved following fluid motions. The angular momentum is related to the radius from the center of rotation, the tangential velocity of the fluid around that center, and the latitude at which the motions are occurring. In order for flow moving inward radially toward a vortex center to conserve angular momentum, denoted here as m, its tangential velocity, which is v in this equation, must increase. This implies that for a vortex to spin up, surfaces of constant angular momentum must move inward toward a vortex center. We'll discuss a couple of proposed mechanisms for TC spin-up and intensification, concepts upon which numerous, more complicated theories have been developed. The first is known as conditional instability of the second kind, or SISK. The basic secondary circulation of a TC is shown here. Generally, angular momentum is conserved along the radial inflow and for ascent in the eye wall. However, in the boundary layer, which is located beneath the dashed line in this figure, angular momentum is not conserved following the radial inflow because friction reduces the fluid velocity, causing convergence of the radial inflow and supporting vertical motion. Essentially, the notion of SISK is that a positive feedback exists between the in-cloud latent heating and the boundary layer convergence that indirectly supports more latent heating. The red area denotes where latent heat release occurs in cloud. This could be in an eyewall-like cloud or just in less organized deep convection located near the center of a developing vortex. This blue line over here represents crudely what the profile of latent heating would look like. Its maximum occurs in the middle troposphere, with the maximum horizontal gradient in heating, or the maximum radial gradient in heating, therefore occurring at this same level. Inflow is present beneath the heating maximum, and the strength of the inflow is dependent upon the magnitude of the radial gradient of heating. And then Coriolis, acting on the radial inflow, increases the tangential wind. And so the radial inflow responds by becoming stronger. The friction increases as the radial inflow increases in magnitude, thus the moisture convergence down here increases. Vertical motions strengthen and latent heat release is enhanced in the cloud. Thus, the radial gradient and latent heating would further increase, forming a feedback loop. As this occurs, the tangential wind is also an approximate gradient wind balance, and as the tangential wind increases, the flow moves inward to conserve angular momentum. This corresponds with an increase in the pressure gradient in the core of the storm. The steps just outlined are listed here. One of the central arguments against SISK as a viable mechanism for explaining the intensification of TCs is that the closure for the SISK problem mathematically implies that the heating rate in convection is directly related to the moisture convergence in the boundary layer beneath the convection. However, the presence of water at spatial scales larger than that of convection does not itself cause convection. The stress is on the word cause there. However, SISK assumes that the increased boundary layer water supply essentially causes convection. Furthermore, SISK does not consider the important role of surface fluxes of energy from the ocean to the atmospheric boundary layer. An adjustment to SISK, known as the cooperative intensification mechanism, prevents a runaway feedback mechanism by allowing convection to stabilize the atmosphere and by gradually reducing flux between the ocean and atmosphere as the boundary layer becomes saturated. But in its original form, SISK is not considered an appropriate explanation for TC spin-up and intensification. However, it does successfully capture a couple of fundamental important points. First, spin-up occurs as angular momentum surfaces are converged above the boundary layer, And the boundary layer, second, the boundary layer is a source of moist static energy to convective updrafts near the vortex center. An alternative mechanism considers the role of surface moisture fluxes in intensification. It is known as wind-induced surface heat exchange, or WISHY. It describes a feedback between surface heat fluxes and wind speed. Recall from earlier in the quarter how heat fluxes between the ocean and atmosphere increase with increasing wind speed. Essentially, fluxes of energy to the atmosphere result in increases in wind speed, which result in further enhanced flux of energy to the atmosphere in the WISHY mechanism. Let's examine this in more detail. First, let's presume that the mixing ratio in the core region of the cyclone is increased for some reason. In other words, this Q sub V right here. That reason might relate to surface fluxes of energy from the ocean to the atmosphere, which is a function of the difference between the saturation specific humidity of the air given the ocean temperature and the actual specific humidity of the boundary layer air just above the ocean. Any increase in moisture is going to lead to an increase in the radial gradient in humidity in the boundary layer, and thus also an increase in the radial gradient of theta E in the boundary layer, since theta E is related to the amount of moisture present. Convection in the core of the vortex lifts the theta E rich air from the boundary layer, increasing the radial gradient of theta E in the core of the storm. This means that theta E increases in the eye wall relative to surrounding areas. By thermal wind balance, this means that the magnitude of the vertical gradient of the tangential wind must increase, leading to an increased tangential wind near the top of the boundary layer. Presumably, this increased momentum is mixed down to the surface via turbulence, where it corresponds with an increase in surface wind. Fluxes are directly related to the magnitude of the surface wind, so assuming no change in the sea surface temperature, the increased wind will cause increased surface fluxes of moisture, thereby continuing the feedback loop. And you can recall again our definitions of surface latent and sensible heat flux from a previous module. Eventually, if the sea surface temperature and the boundary layer temperature equilibrate, this would be the sea surface temperature and this would be the boundary layer temperature, the flux will go to zero, which is one way the WISHY feedback process can be terminated. This might happen, for example, if a tropical cyclone remains over an area for a long period of time, thereby significantly cooling the sea surface. We'll return to explaining another governor on the intensity of a TC shortly. Recent numerical simulations have shown that even with dramatically reduced surface fluxes, intensification can still occur. In this figure, 3 plots of TC maximum tangential winds are plotted as a function of time in the numerical simulation. 3 numerical experiments were run. In the first, denoted by the red line, fluxes were allowed to vary with winds as previously shown. In the other 2 experiments, the green and the blue line, wind speeds in the bulk flux equations were reduced to caps of 10 meters per second and 5 meters per second for the green and blue lines respectively. So 10 meters per second, 5 meters per second is the maximum winds allowed in this equation, even if the maximum winds of the tropical cyclone were higher. However, despite the cap in surface fluxes, rapid intensification still occurred in all 3 simulations, in between these 2 dashed lines right here. The maximum intensities by the end of the simulation were dependent upon the surface fluxes. In the one with just the 5 meter cap on winds, the maximum wind speed got up to just under 40 meters per second, while for the one with the fluxes that were not tweaked, the maximum intensity gets close to 60 meters per second. However, the process of rapid intensification did not seem to depend much on the WISHY mechanism. Therefore, while the surface fluxes are important for setting the maximum intensity of a cyclone, they're not necessarily of first-order importance for describing the rate of intensification to get to that maximum. Vortical hot towers have been proposed as one alternative pathway through which vorticity is coalesced within a vortex core, possibly contributing to rapid intensification. The paper discussion for this week focuses on the evolution of local vorticity maxima in a numerical simulation of a developing TC. The short animation here shows a trim overpass of Hurricane Rita over the Gulf of Mexico in 2005. The red colors indicate the deepest convection, some of which is located in the inner eye wall. These are often seen in developing TCs near the center of its vortex before intensification occurs, and is indicative of the release of latent heat. In strongly rotating towers, such as these, gravity waves cannot easily disperse the heating outward, and the added temperature anomaly is thought to support intense convection. Deep convection, like that seen here, are sometimes also associated with lightning in TCs. Radar observations of one such tower are shown here. They are derived from aircraft data collected in developing Hurricane Ophelia in 2005. The bottom right shows several quantities. Relative vorticity is the colored shading, and is derived from radar-derived wind vectors, with the red colors indicating the largest values. The 35 dBz reflectivity contour is denoted by the red line. Virtual potential temperature anomalies are denoted by white contours, and the two-dimensional wind vectors are denoted by the arrows. This shows an example of deep convection in which the updraft, which is going to be right in here where the potential temperature, the theta V anomalies are largest, is closely co-located with a maximum in the vorticity, denoted by the red colors in the shading. Large temperature anomaly, 4 degrees C or more, develops in the convection. Vertical cross-sections through the same cell are shown at top, with reflectivity shaded in the top panel and mass transport shaded in the middle panel here. These reinforce the notion that this convective element was intense and vorticity rich. In our paper discussion this week, we'll see how neighboring hot towers can merge in the early stages of TC development, contributing to the spin-up of a larger vortex, which offers an alternative hypothesis to SISK and Wishy for how the initial intensification of a TC occurs. Finally, we'll wrap up with a discussion of how surface fluxes and boundary layer frictional flow might govern the maximum intensity of a tropical cyclone. The secondary circulation of a tropical cyclone, when idealized, can be thought of as a Carnot heat engine. The Carnot engine consists of 4 cyclical steps, and the maximum wind speed at the surface is related to the difference between surface and outflow temperature, and the difference between near-surface enthalpy and saturation enthalpy given the sea surface temperature. Eventually, frictional dissipation of energy in the boundary layer cancels out the energy flux from the ocean to the atmosphere as the wind speed increases. Thus, boundary layer friction acts as a governor on intensity in the Wishy mechanism. The Carnot cycle consists of 4 phases. The first, isothermal expansion, occurs along the segment AB in this diagram. Along this segment, the temperature of radially inflowing air remains nearly constant. However, the pressure decreases moving toward the center. Following the ideal gas law, this means that the volume must increase, thus the expansion. Segment B to C reflects the isentropic ascent in convection and divergent flow outward away from the vortex center at upper levels. This is the isentropic or adiabatic expansion stage of the Carnot cycle. During this period, theta E is conserved approximately, and air expands as it rises. The temperature cools adiabatically and reaches some outflow temperature, which is important for computing the efficiency of the engine. This thermodynamic efficiency and the maximum wind speed in the boundary layer is related to the difference between the outflow temperature and the inflow temperature in the boundary layer. Segments CD and DA are isothermal and isentropic compression stages. However, the assumption that isothermal compression actually occurs in the lower stratosphere from C to D has been brought into question. Maps of theoretical maximum potential intensity are created using this method and generally correspond closely with sea surface temperature as seen here. In this example, the ocean surface supports a theoretical maximum potential intensity of about 180 knots, where the dark blue/black colors are. Tropical cyclones rarely reach their maximum potential intensities, however, because environmental factors prevent continued intensification of a storm. Also, internal factors such as eyewall replacement cycles also govern intensity of a cyclone on timescales of hours to days. An example of how minimum pressure varies as a function of boundary layer and outflow temperatures, given a relative humidity at low levels of 80%, is shown here. As you can see, the minimum pressure, denoted by these numbers, generally decreases as the difference between the two temperatures, the surface temperature on the y-axis and the outflow temperature on the x-axis, becomes larger. Eventually, we reach simply theoretical intensities that correspond with temperatures that are not observed, such as really high sea surface temperatures or really cold outflow temperatures at the top of the troposphere. We end this discussion with a caveat. Winds in the boundary layer are not in gradient wind balance because they are subject to friction, although Wishy assumes a vortex and gradient wind balance. This unbalanced flow alters how surface winds and wind speeds in the boundary layer interact, especially in the inner core of a tropical cyclone, denoted by region A here. This is where the flow is also strongest. So unbalanced flow in the boundary layer must be considered when considering intensification of a tropical vortex. But we'll leave these details for a more advanced course or discussion.